What I'd like to describe the basics of our technology, which consists of taking an oxygen sensing dye, or it's almost like a pigment, which I have a bottle here. This is mixed with polymer, raw resin, and this can be compounded together in standard manufacturing practices for making master batches for then extrusion into thin film laminates. But I've got an example here of two different dyes that I'm showing you. They are distinctively different colors. They're different oxygen sensing compounds which we've selected for their different properties, and each has been introduced as I call it, at least a small example of a master batch, where it is by melt process mixed with polymer. And then, as I was referring to, the polymer can be extruded into rolls of thin film, multi-layer laminates, barrier films, etc. This is one example, and we have many other examples. I wanted to show you a quick demonstration of properties of the luminescence of this material. Here I've got a UV laser, more in the way of the blue spectrum. It shows the red emission that occurs from the dye itself. I wanted to show the modulation as I blow from this tubing stream of pure nitrogen gas across the polymer, and you can just see the change, the increase in the luminescence and in the phosphorescence or lifetime of the dye as it's responding to the low oxygen dot, or film actually in this case, is getting brighter due to the displacement of the oxygen by the nitrogen in our little test chamber here. Now, as it has responded to a low oxygen environment, if the package had a leak or a breach in it, hole, and the oxygen is allowed to get into the inside of the package, the response is going to die away just like that. You can easily tell now under the black light where you can see all three of them simultaneously. This bright one here is the low oxygen, and this is the normal air. And I believe we could even further having given you some visual demonstrations of the responsivity of films and different configurations that we've created, I want to now show you indeed how the films can perform as we analyze with our instrumentation here with the optical reading of, I've got a particular film here that's, you can't even see the oxygen sensing dye that's contained within this polymer. It's a multi-layer laminate, but I have a sample here of that created into a pouch that's sealed and has been filled with nitrogen gas, and we're doing a measurement of it right now. First is I'm going to take and remove the tape that's covering the hole on the bag, and that's where the nitrogen was injected into the bag. We'll just let it sit there and leave it for a couple of minutes. Our signal over here now is showing a couple of % oxygen. It's been continuously monitoring this trend line of the oxygen going up inside the package. Wanted to show this to demonstrate that we think it's entirely practical and feasible to ultimately have just a little handheld portable type scanner like you would see in your warehouses and grocery stores and so forth now for doing barcode reading and other types of handheld scanning. Quite practical even to have wireless technology with today, being able to take signal and transmit it anywhere in the world to do your tracking of package integrity. This technology being able to monitor quality of packages both from a map standpoint, and the same is really true with vacuum as well. We've perfected this to the point where you can be reading off of the package, an offset of several inches here actually between the surface being measured and our optical instrument, giving one a great deal of latitude as to how the reading is conducted. And in an automated manner, the reader could be sitting under the package or over it, as we have here, as packages move underneath. If you had say an automated line that you were wanting to do your package scanning on. But in summary, we are presenting here a game-changing technology for raising the standard of package quality, package efficiency, and safety. Thank you very much for listening to our presentation.